Beneath your feet right now is an almost incomprehensible amount of energy, heat left over from Earth's formation 4.5 billion years ago, combined with ongoing radioactive decay happening deep in the crust. The total heat content of our planet is estimated at 10 to the 31st joules. That's several orders of magnitude greater than all the energy humanity uses in a year. The question isn't whether the energy exists, it's whether we can tap into it. That's what geothermal power generation is all about. And unlike solar or wind, it works 24/7, regardless of weather. Let's dig deep, literally, into how we turn Earth's heat into electricity. The definition of geothermal energy starts with understanding where this heat comes from. There are two primary sources. First, primordial heat, energy trapped during Earth's violent formation when planetesimals crashed together and the planet differentiated into core, mantle, and crust. That collision energy is still radiating outward billions of years later. Second, radiogenic heat, energy produced by the continuous radioactive decay of isotopes in the Earth's crust. We're talking about uranium-238, uranium-235, thorium-232, and potassium-40. These elements are concentrated in granitic rocks, and their half-lives range from 700 million to 14 billion years. They're essentially natural nuclear reactors, heating the planet from within. This heat flows from the core, where temperatures exceed 5,000 degrees Celsius, toward the surface through conduction and convection. On average, the temperature increases about 25 to 30 degrees Celsius for every kilometer you go down. This is called the geothermal gradient. But in special geological settings, volcanic arcs, rift zones, places where tectonic plates are pulling apart, this gradient can be hundreds of degrees per kilometer. These geothermal anomalies are where the industry focuses because they're the locations where economic power generation becomes possible. For a geothermal power system to work, you need 5 essential components. Miss any one of these, and you don't have a viable resource. First, the heat source. This is typically a shallow magmatic intrusion. Think magma, just a few kilometers below the surface, or an area where the crust is thin and the natural heat flow is elevated. Second, the reservoir. This is a volume of permeable rock that can hold and transmit fluids. Permeability is critical. It's the rock's ability to let fluids flow through pores and fractures. Many geothermal reservoirs have what's called secondary permeability, meaning the flow pathways were created by tectonic fracturing or chemical dissolution, not the original rock structure. Third, the fluid. Almost always water, acting as the heat carrier. It circulates through the hot rock, absorbs thermal energy, and transports it to the surface. The chemistry of this water matters enormously. It can range from nearly pure to concentrated brines loaded with dissolved salts, silica, and gases like carbon dioxide and hydrogen sulfide. Fourth, the cap rock, an impermeable layer, usually clay or shale, that acts like a lid on a pressure cooker. It traps the hot fluids underground and prevents heat from escaping. This pressure is what keeps water liquid even at temperatures far above its normal boiling point. Fifth, recharge, a source of water to replenish the reservoir, whether through natural infiltration from rainfall or through engineered re-injection of spent fluids. Without recharge, you'd eventually deplete the system. These 5 components define what we call a hydrothermal system, the most common and commercially developed type of geothermal resource. Not all geothermal reservoirs are created equal. The state of the fluid in the reservoir fundamentally determines how you extract power. Vapor-dominated systems are the gold standard. In these rare reservoirs, like the geysers in California or Larderello in Italy, the reservoir is filled primarily with dry steam. When you drill a well, steam comes straight out at high pressure and can be piped directly into a turbine. No separation needed, no complex processing, just pure, powerful steam. These systems are incredibly efficient but represent only about 5% of geothermal sites worldwide. They're geological jackpots. Liquid-dominated systems are much more common, roughly 60% of the global geothermal portfolio. Here, the reservoir contains superheated water under immense pressure. As this water travels up the wellbore toward the surface, the pressure drops. When pressure drops, temperature matters less. Some of that water flashes into steam. At the surface, you run this two-phase mixture through a separator. Steam goes to the turbine to generate electricity. The remaining hot water, called brine, gets re-injected back into the reservoir to maintain pressure and sustainability. This is called a flash steam plant, and it can be single flash or double flash depending on how many times you separate the fluids. The third category is low-temperature liquid systems, typically below 150 degrees Celsius. Until recently, these weren't viable for power generation, but that changed with a binary cycle technology. Binary cycle technology represents one of the biggest shifts in the definition of geothermal power. Traditionally, geothermal meant high-temperature resources over 150 degrees Celsius. Binary plants changed the game by making electricity generation possible at temperatures as low as 70 to 80 degrees Celsius. Here's how it works. The geothermal fluid, the primary fluid, never touches the turbine. Instead, it flows through a heat exchanger where it transfers its thermal energy to a secondary working fluid. This working fluid has a much lower boiling point than water. Think isobutane, pentane, or an ammonia-water mixture. The working fluid vaporizes at the lower temperature, drives the turbine to generate electricity, then gets condensed and recycled in a completely closed loop. The geothermal water, meanwhile, is sent back underground. This technology has expanded geothermal power geographically. Germany, parts of Turkey, the Basin and Range Province in the western United States, regions that lack high-temperature volcanic systems but have abundant moderate heat resources, can now generate power. And because binary plants are closed-loop systems, they have virtually zero emissions of greenhouse gases or other pollutants. They're the cleanest form of geothermal power and represent about 35% of new installations worldwide. Now we get to the most ambitious definition of geothermal power, enhanced geothermal systems, or EGS. This is where the industry is heading, and it fundamentally redefines what we mean by a geothermal resource. Conventional geothermal requires the perfect coincidence of three things: heat, water, and permeability. But what if we could make geothermal work with just heat? That's the EGS concept. You drill into hot, impermeable rock, often crystalline basement rock like granite, that has plenty of heat but no natural pathways for fluid flow. Then you stimulate the rock. You inject high-pressure water to open existing microfractures or create new ones through a process called hydroshearing. This creates an artificial reservoir, a network of connected fractures through which water can flow. Next, you drill a second well into this fractured zone, creating a loop. Cold water goes down one well, circulates through the hot fractured rock, heats up, and comes back up the production well. You've essentially engineered a heat exchanger several kilometers underground. The implications are staggering. If EGS can be scaled economically, geothermal power could be developed almost anywhere on Earth. Heat is ubiquitous. You just have to drill deep enough to find it. This has led people to call EGS heat mining, emphasizing that it's an extractive technology for thermal energy. But EGS comes with challenges. The main concern is induced seismicity, the risk of triggering small earthquakes when you change subsurface pressure and lubricate existing faults. Modern EGS projects use extensive seismic monitoring and traffic light systems. Green means continue, yellow means caution, red means stop injection immediately. Let's talk about how we actually convert heat into electricity. The quality of a geothermal resource is defined by enthalpy, the total heat content of the fluid per unit mass. Low enthalpy resources, below 100 degrees Celsius, are best for direct heating applications or binary cycle generation. Medium enthalpy resources, 100 to 150 degrees Celsius, work well with modern binary technology. High enthalpy resources, above 150 degrees Celsius, are perfect for flash steam turbines and offer the highest thermodynamic efficiency. The basic physics is governed by Carnot efficiency, the theoretical maximum efficiency of any heat engine. It depends on the temperature difference between your hot source and cold sink. The hotter your geothermal fluid, the more electrical energy you can extract from each kilogram of water. In a flash steam plant, the steam quality and pressure determine turbine performance. In a binary plant, the choice of working fluid and heat exchanger design are critical. Either way, We're looking at conversion efficiencies ranging from 10% for low-temperature binary plants to 20% or more for high-temperature flash systems. And here's the critical sustainability piece. Modern geothermal is a circular system. The spent fluid gets re-injected to maintain reservoir pressure and prolong the resource lifetime. This transforms geothermal from simple extraction to thermal energy management. You're not just taking heat out, you're managing a long-term thermal battery. Economically, geothermal is defined by its unique cost structure. Unlike fossil fuel plants where fuel is the primary expense, or solar where manufacturing is the main cost, geothermal is exploration and drilling intensive. The risk is upfront. You might drill 5 exploration wells and only 2 produce commercial quantities of fluid. That's millions of dollars at stake before you generate a single kilowatt hour. This exploration risk is the main barrier to faster deployment. But once a geothermal plant is running, the economics become compelling. The capacity factor, the percentage of time the plant operates at full power, is typically 90% or higher. Compare that to 20 to 30% for solar and 30 to 40% for wind. Geothermal runs 24/7, regardless of weather, time of day, or season. It's baseload power, the steady, reliable electricity that keeps the grid stable. In grid management terms, that consistency is incredibly valuable. Environmentally, geothermal plants emit about 5% of the CO2 of a coal plant. Binary plants emit virtually nothing. The land footprint per megawatt hour is the smallest of any major power source. Most of the infrastructure is underground. Water consumption is minimal, especially in closed-loop binary or EGS systems. You're recycling the same water over and over, unlike cooling towers at conventional power plants that lose water to evaporation. The cutting edge of geothermal power is pushing into extreme conditions. The next frontier is supercritical geothermal systems. When water exceeds 374 degrees Celsius and 22.1 megapascals of pressure, it enters a supercritical state, neither liquid nor gas. Supercritical fluids have the density of a liquid but flow like a gas, and they carry dramatically more energy per unit mass. A single supercritical well could potentially produce 50 megawatts, 10 times the output of a conventional well. The Iceland Deep Drilling Project has successfully tapped into these conditions. If this technology can be scaled, it would revolutionize project economics by drastically reducing the number of wells needed. Another emerging concept is advanced geothermal systems, completely closed loops. Instead of fracturing rock and circulating water through the reservoir, you drill a sealed pipe system deep into hot rock. A heat transfer fluid circulates through the pipes, picks up heat through conduction, and returns to the surface without ever contacting the formation. This eliminates concerns about reservoir permeability, fluid chemistry, scaling, and induced seismicity. It's plug-and-play geothermal that could be deployed in more locations with less geological risk. And here's a fascinating development. Geothermal brines, especially in places like the Salton Sea in California, contain high concentrations of lithium. Modern plants are now extracting green lithium for batteries alongside generating electricity. The geothermal resource becomes a dual commodity, electrons and minerals. Let's look at where this is actually happening at scale. Iceland is the poster child. With 90% of buildings heated geothermally and about 30% of electricity from geothermal sources, Iceland has essentially built its economy on volcanic heat. The country sits on the mid-Atlantic ridge, a divergent plate boundary with exceptional geothermal resources. The geysers in Northern California is the largest geothermal field in the world, with about 1,500 megawatts of installed capacity. It's a vapor-dominated system that's been producing since the 1960s. Indonesia and the Philippines, sitting on the Pacific Ring of Fire, have massive geothermal potential and are rapidly expanding capacity. Kenya, along the East African Rift, is emerging as a geothermal powerhouse in Africa. For direct use applications, Reykjavik heats 95% of its buildings with geothermal energy. Paris uses geothermal for district heating. China has extensive geothermal district heating in northern cities. So what is geothermal power generation? It's the strategic and sustainable management of Earth's internal heat flux for electricity production. It's finding the geological sweet spots where heat, water, and permeability coincide, or increasingly, engineering those conditions ourselves. It's vapor-dominated systems producing dry steam, liquid-dominated systems with flash technology, and binary cycle plants extracting power from moderate temperatures. It's enhanced geothermal systems drilling into hot, dry rock and creating artificial reservoirs. It's supercritical wells tapping into extreme conditions for unprecedented power output. Most importantly, geothermal is baseload renewable power. While solar and wind are intermittent, geothermal runs continuously. As we decarbonize electricity grids globally, that reliability becomes essential. Geothermal provides the stable foundation that allows higher penetration of variable renewables. The resource is enormous and largely untapped. With advancing technology, particularly EGS and supercritical systems, geothermal could potentially be deployed almost anywhere, not just volcanic regions. We're quite literally standing on a solution to the energy transition. The heat is there. The technology is maturing. The question is whether we'll drill deep enough, both literally and metaphorically, to unlock this planetary-scale energy source. If this helped you understand geothermal power, subscribe for more deep dives into energy technology. Next time, we'll explore how enhanced geothermal systems actually create artificial reservoirs miles underground.